So today we will talk about partial discharge measurements. Now there are various techniques for measurement of partial discharge. Some of them are electrical techniques, some of them are non-electrical techniques. We will of course start with electrical techniques, and then we will see why we need to, despite having ways to electrically measure the PD, we often resort to measurement of non-electrical techniques for measurement of PD. Talking about electrical methods for PD measurements, there are some broad categories. Sometimes we measure the individual discharge pulse. We register the individual discharge pulse. Sometimes we find the total integrated loss due to partial discharge. Sometimes we measure the electromagnetic fields due to partial discharge activity. We must remember that apart from electrical currents being involved in a partial discharge, because of the current flowing, there will be electromagnetic radiation. And it is possible to detect the PD by picking up the electromagnetic fields caused by it. Now let us look at the basics of electrical PD detection. So this is your specimen. We've taken a block of the dielectric material. We have a void somewhere in between, and we consider that the capacitance of the void is Cc. Cb and Cb double dash, Cb dashed and Cb double dashed are the capacitances of the dielectric material which is in series with the void, and Ca double dashed and Ca are the capacitances of the materials in parallel with the void. So away from the void, you have just the capacitance of the material between the two electrodes, A and B, and in line with the void, you have Cb dashed, Cb double dashed, as well as Cc. So Cb dashed and Cb double dashed can be clubbed together to give you Cb, Cb being Cb dashed, Cb double dashed, Cb. So it's just the series combination of the two materials on top and on the bottom of Cc. So that is clubbed together as Cb. Ca is the series capacitance of the dielectric material, parallel capacitance of the dielectric material in parallel to the series combination of Cb and Cc. Cc, of course, is the void capacitance. And Vs is the supply voltage which comes across point A and B. As long as there is no discharge of the void, Cc is an open circuit. And we can consider at the point of discharge, the switch S closes, and you can consider Rc to be a resistance in series with Cc, which limits the current flowing at discharge. ICT is the discharge current. So switch S will be controlled by the voltage Vc across the void. As long as the voltage Vc is below the breakdown voltage of the void, there will be no no discharge, no flow of current ICT through this circuit. ICT will be equal to 0. When the voltage applied Vs reaches a value such that the divided voltage Vc across Cc is equal to the breakdown voltage of the void, then the switch can be deemed to have an ICT current flows through the resistor. The resistor RC will also take into account the time period or the time constant of the circuits of the current pulse that flows through this loop, through the RC loop, and it will simulate the time constant of that discharge process. This current cannot be measured because we do not have access to the points across this capacitor. We do not know where the void exists within the material. The void can be anywhere within the material, and we do not have access to the terminals of the void. So therefore, we cannot actually measure ICT. This is something that we need to understand. This discharge current would be generally a very short pulse in the nanosecond region. So what happens is that at the breakdown voltage, a current ICT, which is of nanosecond magnitude, nanosecond duration, very small amplitude, flows through the Cc void, discharges the Cc void, and is limited by Rc. Its shape is also fashioned by Cc and Rc. However, we have no means of measuring this current, and therefore we would have to figure out some other way of estimating or detecting this current pulse through measurement at points to which we do have access. So how do we do that? Now, when the switch S is closed and CC becomes completely charged, the current discharges a charge CC. This charge CC was present on the walls, across the walls of the void, and this quantity of charge is associated with the discharge and is neutralized. Therefore, this charge will be lost for the whole system, and we can estimate this quantity as delta QC, which is the quantity of charge which is implicated in the discharge of the void CC, and del QC will be equal to CC delta VC. So the voltage drop across the terminal AB. Now, because of the voltage drop delta VC across, so you have a voltage drop delta VC across the across the void. You cannot measure this, but a consequence of this voltage drop will also be a fall in the voltage VA. And that can be termed as delta VA, which is equal to CB by CA plus CB into delta VC. And this quantity can be measured. We do have access to the supply voltage supply voltage Vs, that is the voltage that you have across A and B. Supply voltage is what you're supplying, and A to B, the voltage can be measured. We do have access to that. So therefore, the fall in the voltage VA can be measured, and we also note that this drop in voltage is directly linked with the drop in voltage across the void, and the drop in voltage across the void is related to the quantity of charge which is involved in the discharge of the void. So therefore, this delta VA is a negative step voltage with a rise time which depends upon the duration of ICT. Delta VC would be in the range of 10 to the power 2 to 10 to the power 3 volts, but the ratio CB by CA is very small, and moreover it is unknown. So therefore, it would be very difficult to estimate, even though we have access to delta VA, we can measure delta VA, but to relate delta VA to the actual value of delta VC would be very tedious. Even if possible, most of the time it is not going to be possible. So thus, a direct detection of this voltage step by a measurement of the whole input voltage would be a tedious task, and we will not attempt it. So to recapitulate or to summarize what I wanted to say, whenever there is a void which is discharging, the capacitance CC, which simulates the void, will be discharged, resulting in a current ICT flowing from CC to RC. The role of RC in the equivalent circuit. So this is not the real circuit. This is an equivalent circuit which simulates the sample as it is. Now RC, the value of RC is decided. You choose the value of RC to appropriately simulate the magnitude and shape of ICT. It determines the time constant of the discharge. Now, when this ICT current flows, a quantity of charge QC, which was present across the void before discharge, is discharged, and we would like to measure this quantity, and this quantity of charge which is implicated in the discharge is related to the fall in voltage, or the voltage drop across the void. The voltage across the void is VC, and when there is a discharge, it will fall to some value, maybe 0, maybe to a residual voltage VR, as we have seen in the previous lectures. So whatever be, there will be a voltage drop, and that change in voltage across the void is related to the charge that is implicated in the discharge. If we could have measured delta VC, we would have been able to measure delta QC. Now, though we cannot measure delta VC because we do not have access to the terminals across the void, we do have access to the terminals across the entire sample. And delta VC would simultaneously cause a voltage drop across the supply delta VA. So a voltage drop across the points terminal points A and B will result because of the potential difference in potential across the void due to discharge. This is theoretically speaking true. And if we could do that, we could estimate VC, we could estimate QC, we could estimate IC. However, even though delta VC is not very small, because of the ratio of CA and CB, remember CB is the entire dielectric material, and Ca is that which is in series with the void. So because of the ratio Cb and Ca, it is difficult. This will result in a very small potential drop across the supply voltage. And moreover, we do not know the values of these equivalent circuit parameters, CB, Ca, etc. And therefore, it is not really meaningful to try and estimate delta Vc from delta Va. If we measure delta Vc from delta Va, we could find delta Qc. But since we cannot find delta Vc from delta Va, practically speaking, we are not in a position to estimate delta Qc. So we will have to do something else. So therefore, we have the concept of apparent charge. So again, I've drawn this circuit. You have a coupling capacitor. You have the sample. In parallel to the coupling capacitor, you have an impedance. This impedance Z connects the coupling capacitor and the supply voltage. If necessary, this impedance Z may disconnect the coupling capacitor Ck and the test specimen Ct from the voltage source, so that when there is a short duration PD and a very large current flows, the supply will not be affected. The supply will be forced to deliver a very large current. That should not happen, and therefore the role of the impedance Z is to kind of isolate, disconnect the supply from the test specimen at discharge and also the coupling capacitor. So Ck therefore acts as a storage capacitor. Initially from the supply, Ck will be charged to its maximum voltage. Let's say that is Vs, and this behaves like a storage capacitor or a temporary voltage source during the short period of the partial discharge. So what happens is charge begins to build up across Ct, and when the breakdown voltage is reached, Ct will discharge. When Ct discharges, a current It flows through circuit. This current is drawn from the coupling capacitor. So from the coupling capacitor, a quantity of charge Q is drawn, and this Q results in a current It flowing through the cable, through the test specimen. Now, if that is the case, now the PD pulse that flows through the test specimen, we know it's a very short duration pulse. Let's say this PD current pulse is It, and this flows between Ck and Ct. And what is it trying to do? It is trying to cancel the voltage drop delta Va across AB, across the coupling capacitor or across the test specimen. Now, Ct is approximately equal to Ca plus Cb, where Ca and Cb are the the capacitances of the dielectric material, as we have described in the previous slide. So if Ck is much larger than Ct, then delta Va can be completely compensated. So whatever charge delta Q has been lost due to the discharge will be obtained from the coupling capacitor Ck, and it will be given back to the test specimen. So Q will be equal to integration It, which is equal to Ca plus Cb into delta Va. We also know that Q is approximately equal to Cb into delta Vc. So therefore, this is the charge Q which can be measured. This is the charge Q which can be measured across the potential across Ck. So you can measure the potential difference across Ck by measuring the charge that flows in the circuit comprising of Ck and Ct. So you will have a measure of the charge which is involved in the discharge within the volume Cc. That is the discharge of the capacitor Cc. So within the volume of the dielectric, a small discharge takes place, Cc, and we do not know what is the exact quantity of charge which is involved in that discharge, but what we can estimate is, we can estimate the charge Q, which is the integral of the current I. This current I is not the current that is flowing inside the void, but rather it is the current that is flowing in the external circuit, the circuit external to the test specimen, and this current flows from the coupling capacitor to the test specimen. We do have access to this pulse. This will also be a pulsative current, and if we integrate it, we will be able to estimate the quantity of charge which is implicated in the discharge. Now, what we should remember is this quantity Q is not the actual quantity of charge which is involved in the discharge, but this is the quantity of charge which must be replenished from the coupling capacitor Ck to the test specimen Ct as a consequence of the discharge within the void or the capacitor Cc. And therefore, instead of calling it the discharge PD charge, we call it the apparent charge. So the word apparent was introduced because this charge is not equal to the amount of charge locally involved at the site of the discharge or cavity. This will correspond to a certain quantity of charge at the discharge location, and if we knew the size, the parameters, so that we could estimate Ca, Cb, Ct, Cc separately, we would certainly be able to find the exact correlation between Q and the actual charge. However, we don't have the information necessary to obtain this correlation. So what we will do is we will go by the quantity of charge that is supplied by the coupling capacitor due to the discharge happening inside the test specimen. Remember here, the test specimen does not totally discharge. It is only a small void inside the test specimen which is discharging, and as a result, a current pulse is obtained in the external circuit. This integration of this external current pulse gives you the quantity Q, and therefore it is the apparent charge magnitude. So remember, PD is always characterized by an apparent charge quantity or apparent PD magnitude, which is a measure of the PD involved. So as you can imagine, we quantify a PD happening in an insulator, inside an insulator, with a corresponding quantity of charge which flows in the external circuit and not really at the local site of discharge. But that is what is used as the magnitude of PD. So this is very important to understand that this is an apparent charge and not the real charge involved. So apparent charge Q of a PD pulse is that unipolar charge which, if injected within a very short time between the terminals of the test object in a specified test circuit, would give the same reading on the measuring instrument as the PD current itself. The apparent charge is usually expressed in picocoulombs. This apparent charge is not equal to the amount of charge locally involved at the site of the discharge, and it cannot be measured, which cannot be measured directly. So to repeat, there is a certain quantity of charge which is involved at the site of discharge. We cannot measure this, but we characterize a PD pulse by not the real charge at the local site of discharge, but by an apparent charge. And what is that apparent charge? If I had an apparent, if my apparent charge of a PD pulse is Q, it means that if I injected a charge Q across the test specimen, not the void, across the test specimen, then my measuring equipment would give me the same reading as I obtain if a partial discharge has occurred inside the solid material of that particular dimension. It would give me the same reading. So a PD happens, it gives me a particular reading. I say that it has a magnitude QPC, Q picocoulombs. It means that if I take Q picocoulombs and inject that between the test specimen, the total test specimen. Let me go back to the circuit. So I have a discharge happening here, and it involves some charge Q actual. I cannot measure it, but because of this Q actual, in the measuring instrument, I see a certain quantity, a certain magnitude of PD pulse. Let's say that certain quantity of PD pulse I called Q. So what it means is that if I took a Q picocoulombs of charge and injected it between the test specimen between these 2 points, then my reading instrument would show the same magnitude, would show the same magnitude of PD pulse. So here the measuring instrument is important, the circuit is important. You change any of these, you will have to recalculate the apparent charge involved for the same PD. For the same PD, you will get a different quantity of apparent charge if you change any of the quantities. If you change the coupling capacitor, if you change the if you change the measuring equipment, whatever you do. So once the circuit is in place, only then you can say that this quantity of charge is equivalent to this apparent charge in this situation. I will describe later how we take this into account during measurement. But so the definition of apparent charges, it is the quantity of charge which, when injected within a very short time between the terminals of the test object in a specified test circuit, would give the same reading on the measuring instrument as the PD pulse we are talking about. So then we come to PD measurement. This is a standard electrical circuit for PD measurement. You have the test voltage, which is an AC voltage. You have the impedance. I've already talked about it. You have the coupling capacitor. You have the test specimen here. So this CT includes the capacitance of the void and of the entire dielectric material in which it is placed. And then you have a resistor in series with CT. And from across the resistance, you take a signal which is read in a CRO. So, the main contribution of the currents flowing within the branches CK and CT are the displacement currents C dVdt, and both are nearly in phase. You have the branches CK and you have the branches CT, test specimen, the coupling capacitance, and both of them will see displacement current flowing through them, and these two displacement currents in these two branches will be in phase almost. Now, the PD pulse current IT are not only very small in amplitude, but they're also of very short duration. Typically, they're of the nanosecond range in duration, and the amplitude is like 10 to the power minus 4 amperes. So that is the current that would be flowing in the test circuit. So that is the current that will be flowing through the resistor R. So that will result in a voltage across R. The voltage across the CRO input is then given by VMT equal to IT plus I into Z0 R plus Z0. Now, if the capacitance of the test object is very small, only then it would be possible to measure the voltages corresponding to the PD currents distinctly from the displacement current. So you already have a displacement current ITT, and over that is imposed the superimposed the PD pulse current IT. So what you actually have, so IT is the current that flows only when PD pulse flows. But even in the absence of a PD pulse, you have a current IT flowing through the resistance R. And that is because of the displacement current through CT. Now, therefore, to be able to distinguish IT, when IT superimposes on IT, you need to be able to distinguish IT. And IT has a very small magnitude and has a very small displacement. So it is going to be very difficult. So therefore, we would need to insert amplifiers or active voltage probes of very high bandwidth at the input end of the signal cable if we want to be able to detect this current IT pulse which is flowing, and if we wish to observe it in the CRO. Now, this circuit is a what is called a straight detection circuit, and we already see that there is a problem. Straight PD detection circuits are very sensitive to disturbances, and it will not only be affected by, you will not only see in the CRO discharges happening in the test specimen, but if there is any discharge anywhere within the circuit, entire circuit, even inside including the high voltage source, it will be detected by the coupling device, and therefore will kind of mess up with your measurement. So you will have a lot of noise, unintended noise. And therefore, it is very important that the testing transformer, the supply, should be PD free as far as possible. You should also have screening and filtering. High voltage filters or inductors are expensive. We should also make sure that there is no partial discharge in the high voltage leads of the test circuit. So you have these high voltage test leads which come and they are in air. And if you have the slightest protrusion, slightest irregularity of surface, they can discharge, the leads can discharge, and those PD pulses will superimpose on the PD pulses that we actually intend to measure, and it will mess up our measurement. So it is also difficult to avoid any partial discharges at the high voltage leads of the test circuit if the test voltages are very high. And therefore what we do is we have a basic improvement of the straight detection circuit, and sometimes instead of using a straight detection circuit, we use what is called a balance circuit, a bridge circuit. So this bridge circuit is very similar to a sharing bridge. We've not yet discussed the sharing bridge, but a sharing bridge is a bridge circuit where we balance it out and only we measure the imbalances. So this is the basic principle of the bridge detection circuit which is used in PD measurement. You have the voltage as before, you have the coupling capacitor here, you have the test specimen here, and the rest of the circuit you see is now modified to form a bridge. The coupling capacitor CK and the test specimen CT form the high voltage arm of the bridge, and the low voltage arms are very similar to the sharing bridge which we will study later. Now what we do is we adjust the bridge for balance at whatever frequency we want, such that tan delta K is equal to tan delta T. So that means when this condition is fulfilled, you will see null detection, and therefore your circuit is balanced. If even there are some discharges here and there, some imbalances, this will be balanced out in the bridge circuit. It will affect the displacement currents will be there in the arm, CK arm as well as the CT arm, and they will balance each other out when you balance the circuit. This condition is best fulfilled if the same insulation media are used for both capacitors. We need to use a partial PD-free sample for CK. So when we buy coupling capacitors for PD setups, we have to make sure that it is PD-free. And when we say PD-free, of course, you really cannot guarantee that any equipment will not have any PD, but we generally are talking about, when we say PD-free, what we are talking about is the PD magnitudes will be less than 5 PC. And they should be as similar as possible. So the use for partial discharge free sample for CK of the type as used in CT is thus advantageous. So as long as you do not have discharge in the CT, there will be no reading registered at the oscilloscope, and only when and you will have a balanced condition. When you have a PD, that PD pulse will be obtained at the oscilloscope. And generally, if you look at a PD detector, you will see that they use a display like this, where you have an elliptic display, and you can see individual pulses that are playing on the some parts of the ellipse. Now, let me tell you, this ellipse is nothing but the sine wave folded on itself, which means that this part of the ellipse corresponds to some part of the sine. So if you take this ellipse and open it out, what you will see is a sine wave, and this gives you a estimate of the phase at which these PD pulses are being seen. Though this is the kind of display that you generally see, we don't really work with displays like this. We use what are called phase result analysis, or phi-QN plots. What are phi-QN plots? If you look at this sine wave, let's imagine that I have taken this ellipse and I have opened it up, and I have opened it up such that these pulses are here. Now, whenever I register a pulse, I put a mark. And this way I build what is called the phase resolve phi-QN plot. What is the phi-QN plot? Phi is the phase. It is the phase at which the discharge occurs. So counting from the zero crossing, what is the phase at which a particular discharge occurs? As you can see, in this part of the circuit, in this part of the high cycle, you almost see nothing. Whereas most of the pulses are occurring in this part of the sine wave. So let's say this is the opening, the rising slope. So most of the pulses are here. So the phase is given by phi. Q is the magnitude. Magnitude corresponds to the apparent PD discharge PD quantity, apparent charge. So it's given in picocoulombs, and N is the number of pulses. So basically, when you have a phi q n plots like this, what you have, the information that immediately is available to you is that at a phase difference, at a phase of phi I, you have Ni number of discharges of magnitude Qi. And phi qn plots are built up over a large number of cycles. Of course, you have to make sure that over these large number of cycles, the signature does not change. So the phi qn plot gives me a signature of the kind of PD that is happening. The PD is characterized by the phi qn plot that you have on an average n number of pulses of Q magnitude at phase phi. And you have that for every phi. And in order to have a dependable phi qn plot, you will have to take measurement over a very large number of cycles and keep building this phi qn plot, because these PDs are to a large extent statistical in nature. But of course, if you're going to use, let's say if you use 500 cycles to build up a phi qn plot, you have to ensure that within that time period, the nature of the discharge does not change. The PD pattern remains the same and does not mess it up. So this is an example of a phi qn pattern. These are 2D patterns. These are again taken from a paper which is in the public domain. What you can see is these are PD phase patterns for cylindrical cavities in perspex, and depending upon the shape of the cavity, you get a completely different PD pattern shape. The pattern looks completely different when you just visually look at it. The first two are for a square cavity, these two are for the flat cavity, and these two are for a narrow cavity. Narrow cavity means a long cavity, which is the width is low and the length is more. And as you can see, this is the top are the phi's and these are the Q and N. And as you can see, they are quite different even by at look. And earlier we used to work with 2D plots. Now we prefer to work with 3D plots. So you have phi in one direction, you have Q in another direction on another axis, and you have N on the other axis, and you build a three-dimensional plot. And that three-dimensional plot has a particular visual structure. And this we call the signature of the PD, and this signature will change as the parameters of the PD discharge changes. Where is the PD taking place? What is the kind of material? And many other things which we will see later. More the cycles over which we take the measurement, relatively more stable will be the sample period. The cycles should be stable over the sample period, and more the cycles we consider, the better will be the distribution, more accurate will be the phi qn plot that we will build up. So the probability of PD occurring in that particular window will increase. So that's true for any stochastic measure, that if you have a large enough sample, you have more reliable estimates. But we must remember that if you take it over so many cycles, the PD pattern has to be stable over those number of cycles, and the PD pattern should not change.